Hey Ramblers, this video covers chapter 2.3 in our textbook and deals with the derivative as a function. So rather than just focusing on finding the slope of a curve at a point, suppose that we were to graph all of those slopes. In other words, we figure out what the value of the slope of a curve is and then take those numbers and graph a function out of it. That's what this video is going to be about. We're also going to look at what does the sign of the derivative mean. If it's positive, what does it tell us? If it's negative, what does it tell us? And then finally, we'll take a look at some kind of elementary functions like constant functions and linear functions and even power functions. And we'll see if there's some shortcuts we can use to finding the derivative of those functions so that we're not constantly having to take that limit of the difference quotient. Okay, Ramblers, please take good notes. Pause often, and I hope this helps. Let's take this blue function and call it f of x. And f of x, you'll see that we've made these dashed black lines. And those are little tangent lines. They're little lines representing the slope of the curve at that point. And now if we were to set up a table for each x value and what the slope would be at each of those x values, that would be f prime of x. So for instance, when x is negative 2, I can turn to page 91 in my book, page 91, and it will tell me that the estimate for the slope at negative 2 is 6. If I looked at negative 1, the slope is going to be 2. If I looked at x equals 0, that slope is negative 1. If I looked at x equals 1, the slope is negative 2. At 2, the slope would again be negative 2. At 3, my slope is negative 1. At 4, my slope is 1. And at 5, my slope would be 4. So what we're going to do is we're going to take, for each of these x values, we are going to graph the corresponding value of the slope at that x value. And we get, when we do and connect them, another function. So in the second diagram, the second graph, the blue line once again represents f of x, but the black line will be the curve created if we connected all of these order pairs. So negative 2, 6. Negative 1, 2. 0, negative 1. 1, negative 2. 2, negative 2. 3, negative 1. 4, 1. And 5, 4. If you connect all of these points together, we get a new curve, and that new curve is itself a function, and that's f prime of x. Okay, notice that for each x value, there's a value for the derivative. So the derivative is a function. We're going to use that a lot. And then let's take a look now at the original function f of x and what's going on with the derivative at each of those x's. Okay, as we look at the derivative function and the original function on the same axes, we can notice a couple things. First of all, let's look at the original function from negative 2 until about negative 0.5. What do you notice about the derivative? Well, the derivative is positive during that period. And then the function, the original function, begins to decrease. And it decreases from like negative 0.5 all the way to about 3.5. If you can notice, that is the same time that the derivative is negative. The derivative is negative all the way from negative 0.5 to about 3.5. And then the original function, the blue function, begins to increase again. Yeah, the y values are still negative, but the function begins to increase. And that's what we see on the derivative, that the derivative gets positive again at that point. So that brings in a couple of things I want you to put in your notes. If the derivative is greater than 0 on an interval, then the original function is increasing over that interval. That's what we saw from x equals -2 until x equals -0.5. The function, the blue function, was increasing. Notice that entire time the derivative was above the x-axis. The derivative was positive. Okay? If the derivative was negative on an interval, then the function is decreasing. Well, the derivative is negative from -0.5 all the way until x equals 3.5. And during that time, the blue function decreased. Finally, when the derivative was equal to 0, and that means when the derivative crossed the x-axis, like it did at -0.5 and then again at 3.5, we saw on the original function that we had some important things going on. It barely shows up using the chalk I got there, but we have a maximum and a minimum. So they would say that the function is constant over that interval, but we're going to be more explicit that when the derivative is equal to 0, we will have a max or a min when f prime equals 0. Okay, super important to get that in your notes. That's what the derivative tells us about an original function. Okay, let's move on and take a look at some important things to consider in the derivative function. Let's take a look at this example. Now here the graph in blue is the derivative. So can we move backwards from this? Can we sketch the original function? Well, let's say, just for starters, that the original function went through that point right there. Now, since the derivative is negative from 0 until x1, I know that my function must be decreasing. Now, at x sub 1, the derivative is equal to 0. So that means that I have a minimum or a maximum. And since I was decreasing, and then from x1 to x2, it becomes, from x1 all the way to x3, the derivative becomes positive, I know that my function is going to have to start increasing. So let's turn it around and start increasing. Now at x sub 3, the derivative equals 0 again. And so that must mean that I've increased as much as I'm going to, because from x sub 3 until x sub 5, the derivative is negative. So that means my function has to start decreasing. And that is a possible sketch of the original graph, f of x. So I was given f prime, and I guessed what f of x might have looked like based on the derivative. Okay, that's how we're going to interpret the sign of the derivative. Okay, we'll often be asked to calculate the derivative from a table. And here, we can't take the limit as h approaches 0 because we don't have a formula. So we can't do something like this. So we have to do the best we can working with the values we're given. So suppose we were asked to estimate c prime of 0.3. To do that, we could do it a couple of ways. One would be to say c of 0.3 minus c of 0.2 divided by 0.1. And when we did that, we would get 0.4. But another way to have done it would have been to have used c of 0.3 minus c of 0.4 divided by negative 0.1. And if we had done that, we would have found that the derivative had an estimate of 0.2 rather than 0.4. So there is admittedly some error when you are using a table. We can't be sure of the value of the derivative unless we have the formula for the function. Consider a constant function. I don't know. Let's say it's y equals 2. Well, you could think of this function as y equals 0x plus 2. And even though I like point-slope form better, I'm using this because it really points out that the derivative is 0. So if the slope is 0, then the derivative is 0. So that's got to be one of the first things I want in your notes about the derivative value of elementary functions. The derivative of a constant is 0. Now suppose we look at a slightly more interesting function, a linear function. Y equals 2x plus 1, we'll say. Well, here, the slope, again, if we write it in y-intercept form, is going to be very clearly 2. And since that's the slope of the line everywhere, that's also the value of the derivative. So let's make sure we get those two in your notes before looking at the derivative of power functions. Let's take a look at the function y equals, or f of x equals x squared. And let's figure out what would the derivative of that be. Well, we know that to find the derivative, algebraically, we can take the limit as h goes to 0 of x plus h squared minus x squared over h. Now, if we plugged in 0, for h, we'd get 0 over 0, which would tell us to do something. So let's try expanding that numerator. And I get x squared plus 2xh plus h squared minus x squared all over h. And when I simplify that, just as we did in class, we'd see that the x squareds are going to cancel out, and I'm left with 2xh plus h squared over h. Now, when I cancel out the h's, I'm left with a limit that is just 2x plus h. Now, as I take that as h goes to 0, I see that the derivative of x squared is 2x. So, what would the derivative be if I had x cubed? Well, once again, we would take the limit as h approached 0 of x plus h, but this time cubed minus x cubed over h, which is going to equal the limit as h approaches 0. And if I expand x plus h cubed minus x cubed, I'm going to get this expression. X cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Well, several things are going to happen there. Just to save myself the space, I know that the x cubes will cancel, and then each term in the numerator has an h in it, so I can cancel the h in the denominator with each one of these. And so it's going to simplify to equal the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now, as I take that limit as h goes to 0, that's going to equal just 3x squared. All right, so when the function was x cubed, the derivative is 3x squared. Do you see any kind of a pattern here? That when the function was x squared, the derivative was 2x. It's almost like the exponent became the coefficient. And the same thing happened with x cubed. The exponent came down in front and became the coefficient, and the exponent of 3 became an exponent of 2. It does lead us to a rule, which I'm not sure when this book is going to prove to us. I don't think the proof is terribly necessary for you to understand this, but let's get this in your notes. The derivative of a power function, well, is pretty easy to find. If f of x equals x to the n, then the derivative is n times x to the n minus 1. That's a lot of symbols. Let's try an example. So if f of x, let's say, was x to the fifth, then the derivative would simply be 5x to the fourth. So what had been the exponent would become the coefficient, and the former exponent would get decreased by 1. Let's try another example. Let's say we had g of x equals 3x to the fourth. Then the derivative, that 4 is going to come down, but we'll multiply it times 3. So you get 12x to the third, because once again the exponent will decrease by 1. Let's try one more just for good measure. H of x equals 7x to the negative 3. The derivative is going to equal negative 21, because that's 7 times negative 3, x to the negative 4, because this time when I subtract negative 1 from negative 3, it becomes negative 4. Okay, these are really helpful shortcuts and will ease our algebraic burden. Thanks for watching, Ramblers. Hope this helped.